All right, we're actually going to do this here. No meeting. At least right now. Who knows in the next 10 minutes if someone tells me that I'll have a meeting, but we're safe. I think. All right. How's everybody feeling? Can't believe they don't respect the stream. I totally agree. It's like they don't get what I'm doing here, you know? They just don't get it. All right, well, let's go ahead and do what we were planning on doing yesterday, which is continuing to talk about convergence and divergence in terms of our sequences and series. All right, we have various tests so far. We've talked about the nth term test, telescoping series test, geometric series test, okay, P series and a harmonic series. So let's review those a little bit and then also go into our next type of test, which will be the comparison test. Doing well. Living your best life in Animal Crossing. That's good. That's good, you know. Animal Crossing is very important. Probably. Yes. Okay, so first thing that I'm going to do is switch that cube root to 1/3. And then since there's the fourth power on the exponent, or there's an exponent of 4 around that whole fraction, so I could also think of that as 1 to the 4th over n to the 1/3 to the 1/4. And remember, exponent of an exponent, so we multiply, so this should be 1 over n to the 4/3 power. So we should be able to recognize that this is a P series, right? 1 over n to the something. And the actual value of that P, that exponent, is 4/3. So it converges. If I have a P series where the value of P is greater than 1, it will converge. If it's between 0 and 1, then it will diverge. Number 2, same thing. Determine if it converges or diverges. Justify your answer. So I guess, yeah, up here, since it said justify, it converges by the P series test. So we have to give a reason, say how we know, why we know. Okay, so for this series, I'm not certain, so it doesn't look like a P series. It doesn't look like a geometric series. My first, maybe next bet would be to do the nth term test. But I'm going to go ahead, since we're practicing, we're going to use the integral test here. So remember, for the integral test, we need to know a few different things. So we're assuming our f of x is just whatever that sequence was. So in this case, I'll just change it and use x. X e to the negative x squared. So is f positive? Well, we're plugging in the natural numbers. So let me move that down a little bit. Okay. Is f positive? If we're plugging in the natural numbers here, then yeah, if I'm just plugging in positive 1, positive 2, positive 3, then yeah, there's no way that that function will ever give me a negative value. So yes, definitely is positive. Okay, is okay, I think that should be good. I think. All right, cool. So is f decreasing? So we're going to have to take the derivative. So we're going to need to use a quotient rule. Awesome. Okay, it's back. So the bottom times the derivative of the top, that would be 1 minus the top times the derivative of the bottom. So e to the x squared, and then chain rule, so times 2x, divided by bottom squared. So e to the x squared squared. Denominator will always be positive because it's being squared. Now, so if I look at that numerator, I have this same sort of piece, the e to the x squared and the e to the x squared in both. And so think about this as being subtracted between them. So that second term has more stuff in it that's being multiplied by it. right? Because it's not just e to the x squared, then that gets multiplied. Please stop showing up. Then that gets multiplied by x, and it gets multiplied by 2x. So this whole second term will definitely be larger than this first term. So what that tells me is if I subtract them, if I am subtracting a smaller number minus a larger number, that's going to give me a negative value. So I don't care what it is, but I do know that this derivative will always be negative. Now remember, that's because the values of x we're plugging in are always positive. It's the natural numbers, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so yes, this is decreasing. And then lastly, is it continuous? Is f continuous, not the derivative? So the only thing I'd be worried about here is dividing by 0. Right? Maybe because I have this denominator, but e to the power of something, that'll never be 0. Even if I plug in 0 for x, that would still just give me 1 in the denominator. So I don't have to worry about any asymptotes, discontinuities, etc. So this is continuous. So since we've checked those three things, now it means that we are allowed to use the integral test. Okay, so we'll go from 0 to infinity. dx. All right, we'll find this integral. If it converges, then we'll know that the series converges as well. If it diverges, then we'll know that the series diverges. Okay, so since we proved those first three pieces, those first three characteristics are true, then we'll know they either both converge or they both diverge. Looks like it'd be good time for a u substitution. Take the derivative of both sides, so I'd get du equals negative 2x dx, or du dx equals negative 2x, and then I'll just kind of rearrange it a little bit so that I bring the negative 2 over. RJ says good morning and don't ask him for fractions. What did you guys have, a sleepover or something? You guys all at the coffee shop watching this Twitch stream? His chat's not loading. I mean, he can just refresh the page. It would probably work. Whatever. All right, so we'll take this integral now. 0 to infinity of e to the u du, because this just perfectly substitutes for x dx when we do that u substitution. So that works out really nicely for us. So we have negative 1/2 e so the negative, I'll go ahead and substitute back in, negative x squared from 0 to infinity. Guess I should take those off. The refresh worked. Yeah. That's just how it goes, RJ. Okay, so we can't actually plug in infinity, so we'll take a limit here. I'll bring that negative 1/2 in front. And let's replace infinity with b. So 1 over e to the b squared minus 1 over e to the 0th So as b goes to infinity, right, 1 over e to the b squared, so that is all just going to 0 as that denominator gets larger and larger. So all that's left is minus 1 over e to the 0th power, which is just minus 1. Right? E to the 0 is 1, 1 over 1 is 1, negative 1 is negative 1. Okay, so negative 1/2 times negative 1 is positive 1/2. Okay, so we figured out that this limit converges, right? This limit exists. So we know since the limit converges, the series also converges. It really doesn't want me to write today. The series also converges by the integral test. Boom. Right? They both converge or they both diverge. As long as we prove that the function's decreasing, it's greater than 0, and that it's continuous, then we'll know that these limits, or the limit in the series, will do the same thing. All right, so today we're going to talk about the direct comparison test. We're actually probably not going to do the limit comparison test. So the AP College Board, they cut off some things that won't be assessed on the AP exam. And so for this last unit, we're going to kind of skip around. We're not going to do really as much as we normally would if we were here every day. We probably could, since I'm still doing a live stream every day, but I want to focus on the stuff especially that they have said that we should focus on since everything has changed. So we'll kind of jump around. We'll definitely do this direct comparison, but we probably won't do the limit comparison test since they said it won't be as necessary. Okay. But so the direct, so usually we just call it the comparison test. Sometimes it's also referred to as the direct comparison test, because again, there is also a limit comparison test, but whatever. And so that is this. So if we can show that there's some sequence, that an is some sequence that's between 0 and another sequence, okay, then there's two things. There's two big pieces here. right? If the series of Bn converges, then so will the series of An. Or flipped, if the series of An diverges, then so does the series of Bn. Okay, so let's kind of break this down. So let's say I have some graph. So let's say my green dots are Bn. And let's say that these blue dots are An. Okay, so we can see that the blue dots are always less than the green dots, okay, at least for each term, right? Assume they were all perfectly lined up. I kind of botched it on this second one. Right, the blue dots are always less than the green dots. So that's the sequence, right? That's this part. Okay, An is less than Bn. So then if we talk about the series, right, of adding them all together, so let's say I know that this series converges. Now, maybe, how do I know that? Maybe I know that from the p-series test or geometric test or whatever. But if I know that series will converge, and I know that there's this other sequence of ANs that are always less than it, well, then if the series of Bn is converging, it's all going down to reach some value, and I know that the series An is below that, is less than that, well, then it's like, so the comparison is, if I know that Bn is going down and converging to some value, well, then it must be forcing An down too. An must also be converging to something, since I know it's less than this thing that is already converging, if that makes sense. Right? Or similar style thinking for this. So I'll still use my same colors. So let's say An is this sequence, and Bn is this sequence. So if I know that those blue dots, right, from some test, if I know those blue dots, the series will diverge, and I know that the green ones are always above it, right, Bn's always above it, well then if An is diverging upward into infinity, well then I know that it's going to push Bn up as well. It must also be diverging, since I know that it's greater than An. Okay, in that order specifically. I'm not entirely sure what you mean by in that order specifically, but it just means that whichever one is less, I guess it is this order specifically, right? It just depends on which way we're talking about it, right? There's kind of like two theorems here, or two rules. So An is between 0 and Bn. So if that outer one is converging, right, if Bn is converging, then yes, An will also converge. If that inner one is diverging and Bn is larger than it, then it must also be diverging. Kind of seems like the squeeze theorem for series. Yes, 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 yes. Very similar thinking. Yeah, definitely. That's a good connection. Right, the squeeze theorem told us, oh, come on. Right, the squeeze theorem told us, like, if I know this green line or this green curve is always between the red curve and the blue curve, and if the red and blue curve both equal this limit at this point, then I know the green one has to as well, because it's forced in between it, so that must also be the same limit there. So yeah, kind of very similar to the style of thinking to the squeeze theorem. It's a good connection. Okay, so let's actually use this and see how it works. All right. So we're gonna have to we're gonna take our functions and we're just gonna pick things that we know how to figure out if they converge or diverge. Right? And we're gonna have to be able to know, wait a minute, which of these is a larger sequence, right? Because the whole thing is based on, do we know which sequence is larger than the other one? Which one's smaller? Okay. So for example, which is larger? Okay, well this one should be easy. Right? That 3 to the n is less than if I had 3 to the n plus 2. Okay, but then when we think of that then as a fraction, right, the reciprocals of those, that it is the other way. Right, so the larger denominator means a smaller fraction. Okay, so just in the same way that 4 is less than 5, but if I think about 1/4 and 1/5, well, 1/4 is larger than 1/5. Okay, or at least that's what RJ told me whenever his chat was working. Okay, so keep this in mind because we're going to have to use this type of thinking a lot of, okay, wait, this denominator or this numerator is larger, so that means this, fraction or reciprocal, etc. But we need to know how to prove something is larger, greater than, or less than. That way we can apply the comparison test so that we can compare the two. So 1 over 2 plus 3 to the n. All right. If I did the nth term test here, I would get that the limit is 0. Right? So again, we don't, well, I'll just go ahead and do it. All right, a good starting spot is always, well, what's the nth term? Let's take the limit of the sequence. Well, that limit is 0. So remember, for the nth term test, if we get 0, that's inconclusive. Right? We don't know. It doesn't tell us if it diverges or converges if we get specifically 0. If we got some actual value, like 2, 3, 1/2, 1/5, 2,000, then I would know, oh, okay, this series diverges. But since we get 0 specifically, then the nth term test, inconclusive, doesn't work for us. This isn't a P series. It's not a geometric series, at least right now. It's not telescoping. So let's instead try to use the comparison test. All right, so interestingly, if it would let me write in green, like we talked about on our last screen, 1 over 2 plus 3 to the n, if I compare that to 3 to the n, right, it's less than 1 over 3 to the n. Okay, so now what I'm thinking is, great, then if I can prove that this converges, that would also prove that my original would converge, right, by the comparison test. And this will also be always greater than 0, right? And that's part of it. So let's instead look at this series. Well, another way that I could write that is 1/3 to the n. And I'm kind of excited now because this is looking a little bit familiar to me. And if I do one more thing, so I should hopefully recognize already, but if I make one more change, so if I pull a 1/3 out, hopefully we recognize that this is a geometric series. Right? Geometric series are of the form a times r to the n minus 1. That's exactly what we have here. So a is 1/3. R is also 1/3 in this case, and then the n minus 1. So now I just need to think back to my geometric series test. And the geometric series test tells us just look at what R is. And more specifically, look at the absolute value. So the absolute value of 1/3, that is less than 1. So it converges. Right? If R is something that is less than 1, then it'll converge. And now, so we know this series converges. We know our 1/2 plus 3 to the n is always less than 1/3 to the n. So if 1/3 to the n, that series is converging, then it's forcing down that series that is less than that as well. So I know that that will also converge. And that is by the comparison test. Right? The series of the larger sequence converges. So I know then that the series of that smaller sequence will also converge. And in the midst there, we had to use our knowledge of geometric series to prove that that series converged. And again, and we might have to use, a little bit of manipulation. Things aren't always exactly how we want them to be. Like we started here, had to make a couple changes, so I said, oh, okay, yeah, actually it is a geometric series. Okay. Let's try another. So 1/9 negative 2 plus square root of n. Okay. Wait, I lost my notes. Hold on. Okay. So same thing. If I did the nth term test, if I just took the limit of this, it would be 0. And that doesn't help me. That's inconclusive. So I need to use some other type of test. This doesn't look geometric at the moment. It doesn't look like a p-series at the moment. Doesn't look like telescoping. So let's instead try to use a comparison test, because what I do see is if this series were just 1 over square root of n, that is in the form of a p-series. Okay, so I think maybe I can compare here, because I can think of this as 1 over negative 2 plus n to the 1/2. Okay, so let me think about comparing this. 1 over negative 2 plus n to the 1/2. And if I compare that to 1 over n to the 1/2 power, so first, if it's very common, so I know this, I don't know. It seems like one of those things that is very simple and that you can just immediately figure out, but double check yourself, right? Because often people kind of go quickly through this part and screw it up. Okay, so first think about just which denominator would be larger. Okay, well, we have n to the 1/2 over here, and then we have n to the 1/2 minus 2. Okay, so this denominator would be larger, right? But if that denominator is larger, then that means the fraction, when I take the reciprocal, means that this entire fraction is larger than the right side. Okay, so we kind of have to go through that process, right? A larger denominator means a smaller overall number. Okay, and again, think of just like 1/4 and 1/5. 5 is a larger number, but that means that 1/4 is larger than 1/5. Okay, same thing here. Okay, so since it's less than, so if I could show that this diverges, then it would also prove that this diverges. Right? That right side is less than the left side, but if that right side, that series is diverging to infinity, and the left side's always larger than the right side, well then it'll also be forced to definitely diverge into infinity as well. Okay, so let's see what I can figure out about 1 over n to the 1/2 power. I should note immediately that this is a p-series, right? 1 over n to the power of p. P in this case equals 1/2. Which means the series diverges. Okay. So like I just said, so if I think this is my doctor. Hold on a second. Bad news, guys. They said I'll never see again. They have to amputate my eyes. It's tough. It's tough. Starting right now, yeah. In 10 minutes, the doctor's going to show up at my door. And, well, actually, just going to show up outside my window. And they're going to fire a bow and arrow just right through the old eyes. How are you going to do math? I'll just feel it, you know. I can feel the math in my heart and know what the problem still will be and what the answers should be. Braille math. Yeah, well, people do it. Okay, sorry about that. That could happen again. I don't know. They're calling me back again at some point, but sorry. Where was I? Yes. Okay. So this larger series this smaller series diverges. So that must mean the larger series will also diverge. And that is by the comparison test. All right, so the comparison test is really all about being able to look at the original series and see that there is another series, or there's a more recognizable series within that. All right, so like I said up here, I first had to recognize that if it were just 1 over square root of n, that's a series that I could figure out, right? That's a p series. Or same thing on this last problem, I first had to recognize that if the series were just this, that I could turn that into a geometric series, something that I know. All right, so we just had to get rid of the 2 or the negative 2, etc. Right, so we have to have the knowledge of those other types of series in our brains so that we can say, oh yeah, if I just compare it to this, I can figure out if that diverges or converges because it is a whatever series, P series, it's a telescoping series, it's a harmonic series, it's a, etc. Is this going okay? I feel this is one of those things where, I've never taught it before, and so I feel like I'm kind of ranting more or rambling more than I should. I could probably be saying things more concisely, but I'm just not used to, so I've never had to do it. I just realized you were writing so before that instead of an S of O. Yeah, just so. So the series also diverges. Good stuff, Reese. Reese, did you also have a doctor amputate your eyes, or is that just me? So you had 4 before, or 5 before. Okay. All right, determine the convergence of the series. Justify your answer. All right, again. I'm feeling math vibes, not English ones. Right. Well, you guys have a Socratic seminar coming up later today, right? You can't spell? Come on, you can do it. Moderators, please ban anybody that misspells a word. Okay, for this series, from 0 to infinity of 4 to the n over 5 to the n plus 3. Okay, so I don't know anyway immediately that I can see that I could figure out this if this converges or diverges just from one of my other tests. But I am interested in 4 to the n over 5 to the n. Okay, so let me compare. Oops, not 5 to the n plus 3, 5 to the n and then plus 3. So if I compare that to just 4 to the n over 5 to the n, so that left side will have a larger denominator because it's plus 3. So a larger denominator means a smaller number. Okay. So what that means is if I can prove that this right side converges, then that means my original series must also converge. All right, if I can prove that the series of the right side converges, then that means the series of the left side must also converge, since the left side is less than. Okay, so let's do this. Now the first thing I'm going to note, so 4 to the n over 5 to the n, is that actually I could write that as 4/5 to the nth power. And I would say this almost looks like a geometric series. It's not quite in that perfect form. So remember, a geometric series, we started at n equals 1. So let me fix that. So we've done this once before I can't remember when exactly it was, but we did this in a lesson before where if I want that bottom number to be a 1, so I'm bumping it up from 0 to 1. So to account for that, in my formula, I'll do n minus 1. So these two series are still exactly the same. I just changed how I wrote it so that it's in the correct form that I want. All right, if I bump that bottom number up 1, well, then I need to fix that. I need to account for that by subtracting 1 in the actual equation. All right, so it all evens out. This is now in the form of a geometric series where that coefficient is just 1, which is fine. That could happen. And r, my ratio, is 4/5. Four-fifths is less than 1, or the absolute value of 4/5 is less than 1. Which means that that series converges because of the geometric series test. Right? So if this series converges, and we know that our original series must be less than that, then it must also converge. Let's see, let's use blue. So, aka S of 0, five to the n plus 3. Yes, plus 3. It also converges also by the comparison test. Okay, questions about the comparison test, about this specific example or previous example or the test in general? Again, I think it does make pretty decent intuitive sense if I'm explaining it well, which there's no guarantee that I am. Because again, I think I'm saying things in a lot more words than are probably needed. But it's just about what's figuring out what's greater than or less than other things, and then using our knowledge of one of those. If I know this one can converge or this one can diverge, then could that potentially force the other one to converge or diverge as well? But it assumes that we have those other tests on lockdown. All right, we know how to use the geometric series test. We know how to use the p-series test. If needed, we know how to use the integral test or the nth term test. Again, the nth term test is a good place to start. But if you get 0 or if you don't get an actual answer at all, like if you get a divergence, then the nth term test is inconclusive. So it's hard to say. Okay, I'm getting nothing from you, so I assume that means you're perfectly understanding this. Okay. Here's some practice. Okay, 5 through 10 is using comparison test, and 27 through 34 is kind of like, I'm pretty sure, at least if I remember correctly, because this was from yesterday, it's just kind of a summary where it says, like, determine if it converges or diverges by any test, so out of any of the tests we've talked about. There's a couple people, at least when I last looked, a couple people that still haven't finished those multiple choice questions from the AP website. Okay, please do that. I'll be updating on Summit today. Okay, again, that's a checkpoint on Summit, so that is required. Please do those multiple choice questions. I don't think it'll take you an extremely long time. There's like 10 of them. And PFAs, go through, request them whenever you feel like you're ready, and I will approve them. I'm scrolling through my classes right now and just approved a few. So Do you know the scores for that multiple choice? Yes, I do. I can see them. Does it? I thought it's supposed to tell you your results. It doesn't tell you. Does it tell you anything when you finish it? Oh, this one didn't. Maybe maybe that was an option that I forgot to check or something. Let me look real quick. Maybe I can change that so that it does show you. Except the AP website is the worst thing in the history of the universe. Far more deadly than coronavirus is the AP College Board. Are you insinuating the AP College Board has killed more than 3,000 in the U.S.? I mean, would you be surprised? I mean, are any of us going to sit here and be shocked if it turns out that AP College Board just, killed over 3,000? Certainly killed my dreams. Well, we've all been there. What? Well, this is being really slow, so maybe I'll just have to keep working on it and get back to you. Yeah, I'll go take a look at that more whenever I can, so I'm just not sitting here wasting your time. But if I can't figure it out how you can see it, then you could just email me and I'll go in and look and tell you what your score was. Steal their brains are great questions. Quarantine 1. Nope. Okay, I think I actually just changed it. I think. Um, all right, yeah. I believe I just updated it so that whenever you do it, you should be at least be able to see your score. I don't know if you can go in and look at each question, but you should be able to see your score that you got. Okay. So again, please, if you have not finished it or started it, there's still a couple of you I'm looking at now that have not. You know who you are. Please go in and do that. I'll be updating that on Summit today for the checkpoint. Yeah. Anything else for me? Nope. Okay. Suppose I will call it quits then. Let me know if you guys have any questions. Please finish your quarantine one multiple choice questions on the AP website and work on practice or work on your PFAs. Go request those. I'll approve them whenever. Get them done. Ask me questions in office hours if you need. Otherwise, I hope you guys have a great day and are just living it up best you can. All right. I'll see you guys tomorrow. Thanks for showing up.